In this lecture, we're going to go over irreversible and reversible processes. So one of the most important uses of the second law of thermodynamics for engineers is to determine the best theoretical performance of a system. Comparing the actual performance with the best theoretical performance can lead to insights about potential improvements. The best performance is evaluated in terms of idealized processes. Idealized processes are distinguished from actual processes that invariably involved irreversibility. So we're going to idealize our system that no irreversibilities exist. So what makes an irreversible process? A process is called irreversible if the system and all parts of its surroundings cannot be exactly restored to their respective initial states after the process has occurred. A process is irreversible if both the systems and the surroundings can be returned to their initial states. The second law can be used to determine whether or not the system and its surroundings can be returned to their initial states after a process has occurred. So the second law can be used to determine whether a given process is reversible or irreversible. That's what we're going to start using it for. Irreversibility normally includes one or more of the following things. We have heat transfer through a finite temperature difference, unrestrained expansion of a gas or liquid to a lower pressure, a spontaneous chemical reaction, spontaneous mixing of matter at different compositions or states. We have friction, electric current flow through a resistor, magnetization, and inelastic deformation. All actual processes involve some form of something listed above. So during a process, a system, if there's irreversibilities present, these irreversibilities can occur within the system. They can occur within the surroundings, or they can occur both in the system and its surroundings. Because of how and where irreversibilities can lie, we're going to divide irreversibilities present into two classes. We have internal irreversibilities. Those are the ones that occur within a system. And we have external irreversibilities. Those are the ones that occur within the surroundings. A process is irreversible when irreversibilities are present within the system and or its surroundings. However, the irreversibility of a process can be demonstrated rigorously using the Kelvin-Planck statement of the second law and the following procedure. So what do? Well, we assume that there is a way to return the system and the surroundings to their respective initial states. And then we show that as a consequence of this assumption, it is possible to devise a cycle that violates the Kelvin-Planck statement. As it is impossible to violate the Kelvin-Planck statement, the assumption that we can return the system and the surroundings to the original state is an error, and our process was irreversible. A reversible process is a process. The process of a system is reversible if the system and all of its parts and the surroundings can be exactly restored to their respective initial states after the process has taken place. All actual processes are irreversible. Reversible processes do not occur. However, certain processes that do occur can be approximated as reversible. For example, a properly designed nozzle. The last class of processes we're going to look at are deemed internally reversible. A reversible process is one for which there are no irreversibilities present within the system or its surroundings. An internally reversible process is one for which there are no irreversibilities within the system. However, irreversibilities may be located within the surroundings. So there's no reversibilities in the system, but there might be irreversibilities in the surroundings. As an example, we're going to consider water being contained within a piston cylinder. It evaporates from saturated liquid to saturated vapor at 100 degrees Celsius. As the water evaporates, it passes through a sequence of equilibrium states while there is heat transfer to the water from the hot gases at 500 degrees Celsius. So if we think of a system that just encloses our liquid water, the water undergoes an internally reversible process. We can boil the water and we can condense the water, so we can return the water back to its initial state. However, such spontaneous heat transfer is by definition an irreversibility, and it is in the surroundings, so it has an external irreversibility. Another one to think of is when placed outside and exposed to the atmosphere, an ice cube melts and it's going to form a thin film of liquid on the ground. Overnight, that liquid freezes, returning to the initial temperature of the ice cube. The water making up the ice cube undergoes internally reversible process. In our next lecture, we're going to further expand the Kelvin-Planck statement and see how we can use it to evaluate the cycles that we introduced in Chapter 2.